So here we are on the 11th, and we've pretty much gotten most of this done. But I do want to show you the. I didn't demo the CodeWarrior IDE on Tuesday, so I'll do that now. We'll talk about that a little bit. There are some things to kind of learn about that, and it's good to do that. So we'll do that, and then I think I'll do that first. So we'll switch to the laptop. So here's what the CodeWarrior IDE looks like. Now the nice thing about the Freedom Board, and I hope this one works. So when you buy one from the parts bin, it doesn't have headers on it. For everything we're doing, you don't actually need headers. But if you do anything else with it, you do. I ordered several thousand headers, so I have headers, and I'll be happy to give them to you. And you can just solder them on. But you don't need to do that for this semester. But if you need them later on, let me know, and I'll give them to you. If you do Micro 2, you need them. But we don't actually need to hook anything up during the semester. When you get it out of the box from Freescale, from NXP, it has new drivers. If you have an old board, it may have legacy drivers. And there's a little bit of a problem with the legacy drivers. And the problem is that the Windows 10 operating system and the Windows 8 operating system cannot talk to a board with the legacy drivers. So you have to go find a computer running 7 or XP in order to talk to the board and reprogram it. And once you can do that with a Windows XP or Windows 7 machine, then you can, and I guess you can also use Vista maybe, then you can go ahead and change the firmware on the board to the updated firmware, and then once you get that done, then you can load on the driver for the IDE. The new boards actually have drivers for the IDE and for MPEG and other things already on, so right out of the box you should be able to program your board no problem. But if you can't, let me know and I'll help you get things fixed up. So I haven't actually checked this board. It's possible this board has a problem, so I don't know. We'll find out. So, okay, so anyway, so you have to connect it with a mini USB plug, not a micro. So it's the one with the little square window on the connector. I don't know if you can see that or not, but so it has that little square window on there. And it's pretty small, but it's not as small as the mini. Now, one of the things that the way the board works is you can put it in what's called bootloader mode by holding down the button and plugging it in. But if it has proper firmware and the proper driver, you don't need to do that. And you only should have to do it one time. So there's what the board looks like, and this one looks like it's I don't know. Doesn't look like it's working. So, this one's probably screwed up. Yeah, well, let's do that. Well, anyway. Yeah, I don't think I brought another one. That's okay. Well, I just kind of don't really need to demo it anyway. I just wanted to kind of show it to you. So anyhow, so on the board, there are several chips. Yeah, I don't know why that was. Let me try one more. Maybe you'll even maybe a little bit. Oh yeah. Oh yeah, it's got some kind of problem. Okay, so you can see so when it's in bootloader mode, it should blink like this. But if it doesn't blink continuously at the fast pace, then it's sending you a message. And if you download the thing on the Freedom Board, you can find what that code means. So I don't know. But anyway, this one probably needs the updated version, and it's probably not going to talk to my Windows 10 machine. And that's fine. So I'll have to see if I can fix that. All right, it's one of the older legacy boards. But I did want to show you a couple things on the board. So we'll not worry about that. So first off, here's the KL25Z chip right there in the middle, and they put it at an angle, which is kind of cute. And then here's a more advanced, this is an M3, that's an M3 core, and this has the M0 Plus. So this is actually an advanced core, smaller chip, fewer pins, and this chip is on there to basically function like the PicKit 3 for your Viva board. So the debugger interface chip is on the board, and that's kind of convenient. There's a voltage regulator over here, a linear regulator that runs the board at 3.3 volts. And then you have over here, you have a RGB LED, which is kind of nice. It's pretty bright, it's pretty snazzy. In fact, it's so bright it's really hard to look at it when it's fired up. And it has a nice diffuser built into it. I would love to have found this footprint for the Viva board, but I don't know I don't know how to get those chips. And they may be kind of expensive. Anyway, so it has two USB ports. The one USB port is to talk to the IDE through this M3 chip. The other port is a true USB port that your KL25Z chip can actually support and drive, including a built-in voltage regulator to deliver 5 volts to that port, so that it would actually support a device that needed 5 volts. I don't know if it'll do half an amp, probably not, but it'll provide something. And then there's several other chips on here. So a couple of chips. So one chip is this one right here, and that chip is the accelerometer, and it says ACCL above it. And so if you use it, the second lab we're going to use that accelerometer. It is hardwired to the KL25Z to the I2C port 0, and so we'll have to configure that in Processor Expert and set all that up, and we'll show you how to do that. And then it also has over here this touch slider, which is kind of cool. I don't know, you can't really see the pattern. Now you can kind of see the pattern. It's it looks like a Parcheesi board or something with two very high equilateral triangles interdigitated with each other. Or maybe it's not, I guess they're right triangles. And what they do, as you move your finger, it does 2 touch buttons it scans through 2 touch buttons, and then it compares the thresholds on the 2, and it can tell you where you are on that touch slider basically. So it's kind of nice, and there's code to support that, and we use that for one of our labs. And then some of these other things, these are just crystal chips that provide a clock for this one and for this one. So it does have a clock, and I can't actually read those. I don't know, maybe we can. Let's say, it's probably upside down. Anybody read that? Yeah, now it is upside down. Okay. Let's see this. Well, I don't know. I thought it had the frequency stamped on it. It doesn't look like it does. But anyway, I'm pretty sure that's a crystal chip that provides the clock to these 2 different chips. Yeah, I can't really read either one of them. It should be. Well, anyway. And then it has these 2-row headers. It has 1 10-pin, 2 8-pins, and a 6-pin, all double row headers. The outside rows are, all the rows are spaced in the exact Arduino pattern. When they laid out the Arduino, they screwed up, and the 2 headers are not spaced properly here. So because of that, these 2 pins are not spaced on 0.1 centers, which really kind of ruins everything. Same thing over here. So it makes it kind of awkward to get things, but anyway, this does have that pin lineup. But it's a double row. The outside row is sort of Arduino compatible, kind of not really, and the inside row has nothing to do with Arduino layout. Okay, so that's that. So let me talk about the IDE a little bit. So here's Code Warrior, and I think what I'll do, this is the, okay, so there's two different modes you can be in this IDE, and it's real easy to get the windows all screwed up and you can't figure out what's happening. If you do that, then you pull down, you go to Window, click on Window, and you do Reset Perspectives. And when you do that, then it resets the perspectives like this. And that's really helpful when you get it all screwed around and you can't fix it. There's this project window up here. There's a commander window down here. There's a console, problems, and printout window here, just like in the MPLAB X. When you compile stuff, sometimes you'll get stuff scrolling through here and telling what's happening. And then up here is where you would see your code. So in this particular one, you can have multiple programs loaded, multiple projects loaded. As long as they're closed, they really don't cause any problem. So let me. I think I can load up the Blink program. It should be in here. Let's see. So let's see. Oh, project. I think we just have to open. Well. I'm not really sure. Let's see, maybe I don't have any more things on this one. Yeah, here it is. Okay. I don't know what that means, but maybe this will play, so. Okay. You know, for some reason I'm super confused about this. Maybe I have to import it. So, yeah. Okay, so I want, should be, let me see. So it has a defined workspace. You can reset the workspace here. So I forget which one's which. So anyway, I think I'm in workspace normal. But let me see if I can figure out which one of these run. So if I open file, which one did it took me to workspace 2. So, okay, so let's see if I import. Where's it taking me to? It's workspace here, but I need workspace 2. And then what did it do with this? Yeah, so we'll do import. No, it should just do that. Let's see if I can do that. Yeah, so then it loads this up and it lets me select it, and then I can import it. And now it shows up in here and opens it up. Okay, so this is the code, sort of the code we looked at the other day. So this is main, and so this is the one that lets us blink the LED. And this is what you're going to do on Friday. And I don't know that this matches exactly the code that's on Blackboard, but anyway, remember that in order to make this work, you have to change these definitions to match the file on Blackboard that tells you where the RGB LED locations are for the Freedom Board, because some of these were set up for the Tower Board. And I don't need this. So you'll need PTB 18, PTB 19, and PTD 1. So anyway, and these definitions up here, you don't even really need these. You could just write the code. This is just to kind of make it cute. Instead of writing GPIO-D underscore pin set output register equals redshift. So this is actually set up for the blue LED. In any event, you could just write this code directly. You don't have to use this red off, red on, and it's really blue, so it's not even named appropriately. Most of the time I just was switching these things around in a hurry, and I didn't go back and just clean it all up and make it perfectly pristine. And then you can do this delay time, and I think delay time, it's a function, and I guess we created this down here, right here, and it's just a for loop. So you don't have to use that. You can just do your own for loop. So there's a bunch of stuff in here that's really not essential. But what you do have to do is you have to configure the ports. And when you configure the ports, we talked about this on Tuesday, you need to do at least generally 4 things, okay? You need to turn on the clock, and in this case, we're turning on the clock to port D. And again, we do the system, the system integration module underscore system clock gate control register 5 or equal. So we're gonna flip 1 bit, leave all the other bits the same, and then we have this mask with a single bit set, which happens to be the bit in the position of for port D. Now, in order for you to see sort of where that comes up, then let me take you over here to the data sheet, and we'll get rid of this, but we'll go to the data sheet, and I have it in the, sorry. And it's also on Blackboard, and it's this, well, there's one for the Freedom Board, but there's not a lot of, there's a fair amount of information there, but you really don't need much of that. But this one, this one is how to use the chip. And so, and it's called this KL25, P80M48S form.pdf. And this is the KL25 subfamily reference manual. This contains the Freescale version, or now the NXP version, of the modules. It doesn't really talk about the core, because remember the core is an ARM core, so you use ARM documentation for that. Okay, but this is the one you really need to refer to most. We already talked about Chapter 10, the multiplex table. And this is where you go down to the multiplex table, and you can look and see, for any particular pin, you can see what that's connected to. And so for instance, so we're going to, well, this won't tell you about any internal connections on the Freedom Board, because this is just about the chip, the KL25Z chip, or that family. And it covers these 4 different package forms and some other stuff. So it's just telling you about the chip. And for any particular pin, you can see all the various functions that it can provide. In Micro 1, we use PTA 1 and 2 for the UART outputs that receive and transmit. And these actually are the same ones that the debug chip uses to talk to the IDE. And so you can actually use these even if you don't hook them up, because they are automatically hooked up through the other processor. But anyway, if you wanted to actually set up something on this chip, you have to go to this table, find what it is you want to use, what module, see what pins it's available on, and what multiplexer setting you have to set. All the GPIO ports are always multiplexer setting 1, okay? So we'll go do this. And then let me also actually, so I wanted to show you about the SIM, the System Integration Module. So if you look at this, that's Chapter 12, System Integration Module, SIM. So if you go to Chapter 12 and you scroll down, you can actually find those registers. And like I said, they're kind of numbered funny. So here it is, System Clock Gate Control Register 5. That's the one we're interested in. There's also Register 4, 6, and 7. There is not a System Clock Gate Control Register 1, 2, or 3, and there isn't anything more than 8. But there are these other systems option registers, system device identification register, flash configuration register, and other stuff. Computer operating properly register, and some other stuff. So I'm going to go into register 5, which is described here. I click on that, and there it is. There's the system clock gate control register 5. And you'll notice there are 5 ports, each with 1 bit that turns on the clock to that port. So you don't really have to go in here and find out what bit it is. In this case, port D is bit 12, but I don't really need to know that. I can just use the mask that is provided for me in the header file. And so if I go back here to the IDE, then what I can see is that I just need to describe my mask, and the mask is system integration module underscore system clock gate control 5 underscore port D underscore mask, and boom, that puts a bit in place. 12 is a 1, so bit 12 is a 1, all the other bits are zeros. I OR equal that with the system integration module system clock gate control register 5, and boom, I've turned on the clock with port D. Okay, so that's how that works. It's complicated, but it's not ridiculous. All right, and then the multiplexer setting. So notice here, I have the multiplexer setting port D underscore pin control register 1. So this is a whole 32-bit register for just pin control register 1. So what does that register look like? Okay, so now we have to go back to the data sheet and go to the port control. Okay, so that's chapter 11. And in chapter 11, we scroll down here, and the one thing we start to find is that we have pin control registers. And it starts with port A, pin control register 0, and it goes all the way to port A, pin control register 32, or probably 31. And then we have these 2 global registers, one for the lower half and one for the upper half. So this does pins 0 through 15, and this does pins 16 through 31. And this allows you to set a whole bunch of pin control register functionality all at once if you want to. It's a little bit of a shorthand thing. You don't have to use these. You can set each individual one if you want. But if you had to set, 8 pins all at once, you might want to use one of these registers. But because of the way it's set up, there's enough things to set that they can't do it in one register. It takes 2 of them to cover all 32 pins. And then now we start, and then there's another single register that has all the interrupt flags. The interrupt flags are individually for each pin in their pin control registers. But you have a global register with 32 bits, 1 bit for each of the pins, and it also mirrors the interrupt service flag for that particular pin, all in one register. That's kind of convenient too. All right, now we have port B. It's exactly the same. Port B pin control register 0 through port B pin control register 31 with a global low and a global high and an interrupt. And then we have C, same thing, and D, same thing, and E, same thing. So that's how that works. And then if we go look at any one of these registers, and they're all described in the same, well, I think they're all described in the same place. Here's what port X underscore pin control register N. So this would apply to any port, A, B, C, or D, or E, and any pin 0 through 31. And here's what the register looks like. Notice it's a 32-bit register, like everything is on this chip, but a whole bunch of those bits don't do anything. So bit 24 is the interrupt service flag. Bits 19, 18, and 17, and 16 are the IRQC. This controls the interrupt function and also the DMA functions. We'll look at that in a second. Then bits 10, 9, and 8 are the multiplexer setting. This is where we set it to the various functions that this pin can subserve. Always, multiplexer setting 1 is GPIO function. But the other functions are different stuff, and by default, these pins are always come up in mode 0, which is the, well, most of them do anyway, which is an analog function. And then some of them don't have an analog function, so their default function is nothing. So you have to set them to a 1 to ever use any of the pins as a GPIO. None of the pins will be GPIO by default. Okay, and then you have 1, 2, 3, 4, 5 additional bits that control some stuff. Pull-ups, drive strings, the static filter stuff, and I forget. I have to look. Don't remember. Okay, so first the interrupts status flag. It's just 1 if the interrupt's detected, and 0 if it's not. And this is what you have to clear in your interrupt routine if you have an interrupt routine for specifically this pin. And you can set up a particular vector for this pin. It's probably for anything in port D, actually. I don't remember how that goes. You don't have 32 vectors for every port though. Maybe you only have one for each port. In any event, that's the flag. And remember that flag is replicated in the global interrupt status flag register for this port, where it would for this pin, well, we don't know what pin this is, it's whatever pin, but if you were interested in pin 17, then you'd look, then this flag would be replicated at pin 17 in that interrupt service flag register for port, whatever it is, A, B, C, D, or E. Okay, now we look at the IRQC. We're not going to spend a lot of time on this, but you can see there are a number of functions, and then some of these bit combinations aren't defined. So there's an interrupt DME request disabled, there's a DMA request on rising edge, falling edge, either edge, and then there's an interrupt with logic 0, rising edge, falling edge, either edge, or logic 1. So that gives you level, rising, falling, or both. It's kind of nice, and that's what this is about. And this is where you turn on the DMA function, but actually how to use it, I'm a little fuzzy on. Then you have the multiplexer setting. So it's just 0 through 7. If it's 0, then the pin will be in analog mode, and if it's 1, it's in GPIO mode, and then everything else is chip and pin specific. And you have to look at that multiplexer table to know what goes in here. And then you have bit 6 is the drive strength enable bit, and low drive, high drive, but there are pins that don't support configurable drive strength, and some of the pins only have low drive strength. They don't have high drive. And then there's the passive filter. This is kind of a glitch filter. Some of them do, some of them don't. A 0's off, 1's on. And then you have the slew rate enable, and that basically changes how fast the pin can respond. And then you have the last 2 bits, 1 and 0, are the pulls. And pin 1 is pull enabled. So if this is off, there's no pull-ups or pull-downs. And then if this is enabled, then you have to look at bit 0. If it's a 1, it's set for pull-down. If it's a 0, it's set for pull-down. If it's a 1, it's set for pull-up. So you can actually do pull-ups up or down. And these pull-ups are a little more powerful than the pull-ups on the PIC board. They're a little more useful. And that's it. That's where that stuff shows up. Okay, now back to the IDE. Okay, so here we have, so this is our multiplexer setting. Now this is kind of a strange syntax here, but it's kind of not really a mask, or I guess it is a mask, but it creates the mask for you on the fly. So it's a little macro, and what it does, it puts the correct bit pattern. So it takes what you put in here, 0, 1, 2, 3, 4, 5, 6, or 7, creates that binary bit pattern, and then puts it in the proper field so that in that pin control register, in this case, yeah, this needs an 18. I don't know why that wasn't there. Anyway, so this the port D underscore pin control register 18. So this sets up pin control register 18 to be a GPIO pin, and since actually it should be port D pin 1. Now that I think about it, not sure. I guess the 1 got deleted somehow. Anyway, so port D pin control register 1, and this sets its multiplexer setting to 001, which is GPIO. Okay, and then you have GPIO D pin set output register, and that R equals with red shift. So up here we made red shift a 1. You don't have to do that. We could have just put a 1 down there, but we created our own little mask. Red shift is a 1, so it's 1 shifted in one place. So it's actually a 1 in the 2 position because it's bit 1, not bit 0. That's always confusing, right? But anyway, so it's bit 1, and so it sets the output high. And the reason it does that is because the LEDs work just like they do on our Viva board. When the output is high, the LED is off. When the output is low, the LED is on. And this is typically how most people program these things. And then we have So that means the LED will be off until we turn it on. And then finally we have the GPIO-D PDDR, and that stands for Pin Data Direction Register. And again, we OR equals that with red shift. That's our mask that identifies bit 1 in our 32-bit field. And I keep killing this, but it keeps coming back. Anyway, what happens then is this just sets it to a it actually sets it to a 1 for output and a 0 for input. So by default, these pin data direction registers are always inputs, and we have to set them for outputs. Unlike the PIC, where 0 is output and 1 is input, in this case, 0 is input and 1 is output. So it's a little backwards, and you can easily get confused. So just remember, it's opposite of the PIC line. And that's all there is to set this up. And then all you have to do then is execute an instruction that says GPIO-D pin clear output register OR equals red shift, and it'll clear that bit and turn on the LED once you've configured. Okay? Is that clear as mud? So you should be able to take your document on Blackboard, and again, we'll look at that one more time maybe so we can see that. And this. So I want you to make sure you know where that is, and then so it is on 1.1 and under the and then it is on under the KL25Z lab. LED locations, it's just a little Word file. And here it tells you for the Freedom Board, red is at PTB 18, green is at PTB 19, blue is at PTD 1. And then if you want to mess with the tower board, there's where those LEDs are. This is an RGB LED, these are individual. Okay? All right. So, so let me go back to the IDE. Okay, so this is your code over here, and once I selected it, then I can, it appears in this window and I can scroll through and look at it. Okay, that's great. And this routine is just the init routine, we call it, and it sets up the ports. Currently, it's only setting up port D. So to fix this, I would have to enter in the additional code to set up port B, and I'd have to set up port B pin control register 18 to be a multiplexer function 1, and pin 19 to be multiplexer function 1. I only have to have one turn on the clock instruction because I turn on the clock to the whole of port B with one instruction, just like this turns the whole port D on. And then it's good practice to go ahead and set the outputs high so that the LEDs aren't on to begin with, and then you can turn them on when your code starts running. But yes, you really don't have to do that. And then but you do have to set the output data direction register for each for the port. And here, just like as in the pin set output register, you cover all 32-bit pin, all 32 pins in that port with this one register. So anywhere there's a 1, you'll set it. And here, anywhere you make it a 0, you will set it for input. And so it's by default 0. Anywhere you make it a 1, it'll be output. And so that's why it does this OR equal thing. So you could set several pins at once in port B if you wanted to do that. You could say GPIO B _, pin data direction register OR equals, and then you could have a 1 at position 18 and a 1 at position 19, and it would set both of those outputs to 1 at the beginning, which would mean the RGB colors green and red would be off, and this would turn the blue color off. But again, so that's how that gets initialized. Okay, so let me talk a little bit more. So once you get all done, you can run it. And the way this works, this isn't going to be able to compile it, but you click this little bug, and main has been changed, say changes, yes, say changes, and then it should compile. And when it compiles, it switches the view. Now, if you get this screen, it means that you're, well, does anybody have their Freedom Board with them? Maybe I'll program somebody's.
I just got one.
Huh?
I just got one.
Oh, you just got it? All right.
Doesn't mean it feels so good.
Here, you can just. Now, this is only going to do the blue LED, but hopefully it'll work. Yeah, you put it in that one. Okay, and it starts off with, it's loaded with some basic code. Yeah, that kind of, it's preloaded with that. Okay, now, if your IDE is able to talk to your board, you should be able to refresh this. Oh, well, okay, it brought up, it also, the new boards work a little differently, so I'll talk about this since this came up. So this is the bootloader, and it instantiates in bootloader mode as a mass storage device. So you can actually go into this SDA info. Okay. Yeah, I'll show it. So the couple of things to notice. One of them is that the green light's on steadily, and that's what it should be when it's talking to the IDE. But it also, so if I click on this SDA info, it brings up this PE Micro website, and it tells me that our bootloader version is 1.12. And as long as you're more than 1. I think 09 was the last one that doesn't work. If you're at least 1.1 or 1.10 or 1.11 or 1.12, you should be good to go. If you're not, then you can go down here into your firmware apps and you can load it up. But again, you can't fix it when you're in a Windows 10 machine if it's not up to at least 1.10 or something. So anyway, so if you have problems with the board, all the new boards, all the ones that have, well, I don't know, this still has the Freescale thing. But it came in an NXP box though, right? So if it comes in an NXP box, it should have the updated firmware. Interestingly, this is still the, let me show it to you. This is still the Freescale. So this is actually the Freescale logo there still. No, you're good. But these, so I think some of them do have the NXP, and it's got the little QR code. It should take you to a website that will tell you about your board. And the software that comes on here actually responds to the touch slider, and also it also changes as you change the accelerometer. So you can see I turn the code to green, and then I do this, and it turns blue. So it's kind of cool. And then you can change the touch slider too, so it responds to both for some reason. All right, anyway, we'll make it a different color. Okay, so now I'm going to program it. So so the older firmware, it could only be in bootloader mode or not. But now this one, it can actually be in both at the same time. And you don't actually have to put the OpenSDA application on; it should work. So you really shouldn't have to mess with this this bootloader part. So just kind of ignore that. So now I'm going to refresh this. Okay, now it sees it. Okay, and then I can retry, and oh, it's gonna flash it. And so now, once it flashes it, it doesn't run it. You'll notice now I'm in the debugger. I can go back and look at the other screen by clicking the C, C++. Oh, you can't, sorry, Mike. So, okay, I'm going to go back to the debugger. I'll run it again. So I'm going to push the little bug here, and that's going to compile it. And so it should go through, it should compile it, and you can see it scrolls all this information down here, and then when it's all compiled and flashed into the Freedom Board, then it gives me this stuff up here. Now if you shrink it down, some of these buttons disappear and they're on pull-down menus. It's nice to have them. And sometimes you get all the buttons here, and sometimes if you shrink this, you'll lose a bunch of these buttons. This is the disassembled code. So if you scroll through this, you can actually see the ARM 3M thumb code, 3VM thumb code that's actually been loaded into the chip and where it's actually been loaded. And you can single step through this if you want. So you don't even have to step through your C code. You can actually step through the assembly code that the C was translated into. All right. And you can see that there's just register references here. All right. So anyway, so whenever you compile, you switch into the debug mode. Note if I click this, I'm back into my original view. But if I click debug, then I go back into the debug view. Now, the program's not running, but it's compiled, and when it's compiled, I get this little green arrow up here, and it's also replicated here, okay? And if I click the green arrow, then it should run the code. And you can see it's blinking the blue LED really fast. That's the idea. So, now, so that's kind of what's working there, okay? And then you can actually, what's really cool is you can go over here, you're in debug mode, so you don't have to specially compile it for that. And I can actually go down here and I can double click and I set a breakpoint there, and it'll give me any context relevant variables. In this case, the value of I is 271, and we happen to be in the scope of I here. And so if I start the green arrow, it'll run once and come back and stop here again. And you can see, notice how every time I run it, oh, you can't see this, sorry. I need two screens. All right, so here I am. Every time I run it, I click on the green arrow, it runs, and it comes back and stops there. Now, your MPLAB X IDE will do this too. But this is just a little more convenient because you don't have to recompile it and go through a bunch of steps. And then all I have to do is click, and I can double click and make it go. I should be able to, maybe I have to right click. Toggle breakpoint. That turns it off. There's also a global thing up here that turns off all the breakpoints. So you have to be careful that that's not on. And so now if I run it, it should just continue to run. And, oh, well, sorry. Yeah. Disable it. Now we should be able to run it. Yeah, and now it's running. See that? Okay. So the breakpoints are really nice, and you may only have one or two of these breakpoints. There's a difference between software and hardware. It's a little confusing, but you can set two of these, but you can't set three. I think you've done that too. And I never know how to. If you double click, it should go away. Well, the old one will go away. I don't know. I'm having trouble with this. Yeah, okay, now it went away. It's a little squirrely. But anyway, you should explore some of these hardware features. And I think if we look at the disassembly, see what happens when we stop it. So we're here, and I think I can set breakpoints over here too. So I could actually do this one. So we can also set breakpoints in the disassembled code, which is kind of nice. And then it'll just keep running. All right, and then when you're done with it, then you can pause it with this and restart it with that, or you can stop it and then you can hit the red square, which terminates the debug section. But notice here, it'll show you in the watch window. It'll automatically show you the variables that are in the scope of wherever you stop it. And again, what do we call this when we can see our code when we're debugging? What's the word for that? It's probably going to be on your file. We call it source level debugging, where it actually gives you your source code, shows you where in your source code you're executing. So it's source code level debugging. So it's very nice. It's very powerful debug. Okay, so I'm going to hit the red square. That's going to terminate the debug routine. and then if I want to go back to my old view, I do this. Now, one of the other things we're going to do is we're going to invoke Processor Expert. You have to do that when you create the project. And I'm going to close this one and now open the accelerometer. So the second lab we'll do will be the accelerometer project. And when we open this, it takes a minute to get it open, and then here are the sources. Now in this case, you can see we've got a number of things. This actually does some Processor Expert stuff, and you'll see that up here. And there's a whole bunch of generated code that shows up here, lots of headers and C files and stuff. And so it's a little bit complicated, but in any event, we can run this code. And what's interesting, so if I go to the main C file, there it is. And then what I'll do, I'm going to go ahead and compile it, and hopefully this will run. And it's going to put me in the debug view, so I switch views whenever I compile. It doesn't run it, I'm in stopped, and I have to hit the green arrow to run the code. But what I'm going to do is I'm going to go down here in main, and I'm going to go scroll down to where it finishes all the axes, and right here I'm going to put in, it looks like there's actually one there already. So I put in a little, there's a little breakpoint right there. And so it should stop and display the 3 axes. So if I actually run this code, it'll run, and it should show me this. Let's see if I can get this right. Yeah, so it shows the 3 axes here, but they're kind of, so my x is minus 96, my y is minus 54, and the x is 4,000. Now, if I turn the board upside down, then, or the z is 4,000, then what it'll do, it'll flip the z-axis, and it should be minus about 4,000. And it depends on how perfectly level you get it. If you were perfectly level, the only acceleration that the accelerometer would show would be the accelerometer due to gravity. So if I change the axis of the board, then all of a sudden, now I should see, I think it's the y-axis I'm on now. So the other axis, I didn't want to do that, I just wanted to run. So now the y-axis shows 4,000 roughly, and the other two are smaller. And then if I stand it on end, same thing. I get the x-axis is 4,000, and then if I make it invert it, then the x-axis has to be minus 4,000 something. And if you wiggle it around, you'll get it totally level. And it's just that one little chip, so you can see here, it's just this one little chip right here that's doing it. And that chip has a dot in the corner, and if you pull down the data sheet, this is a Freescale chip, you'll see on that data sheet that that dot orients it, and that'll tell you which axis is x, which is y, which one's positive and negative, and then z's up and down. And usually, if you can read the top of the chip, then you're looking, then the positive z-axis is down through the chip, perpendicular to the plane of the chip. All right, so that's the accelerometer and the other one. So the only bad thing is, once you program with something else, your cool little demo program goes away. You can, it's on the web someplace. You can reload it if you really wanted to. But all right, so that's it. What's that?
We'll make one better.
Yeah. So anyway, so that's the Freedom Board, and that's pretty much the IDE. When we do Processor Expert, if we go back into this, there's a couple of things that are a little different, and I don't know that we saw those. Yeah, so you can show the views. And in Processor Expert, there's a couple of unique views that we don't have in without Processor Expert. We get this additional window up here that's called, one tab is the component inspector, and the other is the component library. So if you're on in the component library, there's some stuff that's available that Processor Expert will let you do, and there's some board support stuff and various things, and you can select the Freedom Board, and then under that you can select, I think it does the LEDs. I can't remember. Yeah, that's your RGB LED, and that's yeah, that's the green, That's the red, or that's, yeah, and then this is the blue. So you could actually use Processor Expert to set up your LED if you really want to. Well, that says red also. So, that says red. It says green. That says red. That's good. And this says, that's open. Well, I don't know. Okay, so anyway, there are a whole bunch of different things you can connect to. I've only used a few of them. And then there's not just the board support, but there's CPU external, CPU internal. The CPU internal is where we get to the communications, and we do the internal I2C, and that's what connects to the accelerometer. So you'll see this in the lab. So Processor Expert helps you make code. It's very similar to the Microsoft Code Configurer that you may or may not have used in MPLabX. It's a little more difficult, but the basic idea is, and you'll see this when you do Lab 2, is you'll go down here and you'll click, you double click, and then it instantiates it, and then it brings up this. So if it brings up this goofy menu, and then in the menu you have to select all the features, and it can be very complicated and difficult to follow, but we'll walk you through it in the lab guide. Okay, so that's the other thing. And then in this case, I can go back and I can reset the perspective, and it should turn off all those windows and get me back in here. And what's going on? But anyway, so, and when you look at the Processor Expert code, it gives you all this guidance. Like it says, don't write any code past this line. This is the real-time operating system startup code. And up here, it says a bunch of other stuff. Here's where you can, this is the Processor Expert initialization. Don't remove this code. And then write your code here. And one of the things we struggle with for years, this code actually initializes the I2C line, but then we were initializing it again, so we double initialize it, and sometimes it would work, and sometimes it wouldn't, and I pulled my hair out for years trying to find that bug. Okay, so anyway, I think that's probably about all I want to say about that. Okay, a couple other things. I did go through, I tried to go through all the I2C driven 2-line by 16 LCD displays, and I checked them, and they're actually, all the ones that we had in the lab box, I got working just fine. A couple of them require a different slave address, but all the rest of them worked, and I think if there was any other trick. So 2 of them needed a different slave address. I have some other ones that use the reverse headers, but so if anybody needs to use a 2-line by 16 LCD display, you can follow me back to my office and I'll give you one today. You can check one out and use it in your project. And the code on Blackboard should work with it. I think I have like 6 or 7 or maybe 8 that have the standard address of 27, and then I have some that have the address of 20. So, and they all run it, and all the ones I have run at 5 volts. So you have to run them at 5 and use a slave address 27. And if anybody wants to check one of those out, you can do that. All right, let me stop here and give you a chance for some feedback. So how are you doing with your projects? Good, bad? Okay, so I'll be around all day tomorrow. Feel free to come by the office and get help. And a couple things. One, try and attack it a piece at a time. So try and, if you're doing 2 or 3 different things, try and get one thing working first, and then maybe get something else working, and then see if you can kind of combine them. It's really nice, though, to do all the configuration of your ports for your TRIS registers and any initialization values in your ANSEL registers. So TRIS, ANSEL, all the initialization stuff. Make sure you do that in a single routine you call config. That'll really help you. So know that you have to go to config. Now there are some times where we have to change things on the fly. That's okay. If you have to do that, you should make a note in your configuration register that this bit, this configuration bit value is going to be changed on the fly in my main line or in a function, and that way you know that that's going to happen. But what you don't want to do is, maybe, let's say you want to use RC2 as an output. So you just go ahead and set tris_c to 0, 0. Okay, that's great, but now every tris bit is an output. And if you actually wanted to use some of them as inputs, or with a module that requires them to be inputs like the UART module, now you're screwed. So you have to make sure that you keep track of how you configure your ports. If you want to use something as an analog input to your A to D converter, and you go ahead, but you have other pins on that same port you want to use as digital IOs, GPIOs, and you go ahead and just clear the ANSEL register and set it to 0 for that port, now you've turned off your analog input. So make sure you don't shoot yourself in the foot by configuring in multiple places in your program and then have one configuration override another configuration so you think you've done it right and you don't realize you've undone it someplace else. Try and do it all in one location, unless of course you have a situation where you have to change. There are times when we have to say change the tris register from input to output as the software runs, and that's fine. That's totally acceptable. But just make sure you note that in your configuration register that you're going to do that outside of the configuration register. Any questions about that? All right. So does anybody need to come get a 2line/16 I2C display? All right, so if anybody needs one, I'll have them tomorrow as well. All right, any questions on the lab for tomorrow? So if you can get a Freedom board, that's great. Hopefully the IEEE folks will be around in the morning. They kind of know this is coming, and we do have a bunch of boards in I think I bought 100 boards the last time. So anyway. They did raise the price of buck on them, which was kind of irritating. And then we let IEEE make $1 or something. So anyway, but it's not bad for 17 bucks. All right, if no other questions, then I'll let you go a little early, and we'll see you in lab tomorrow.
Shoot. We need to buy that.